Good morning to all of you. In previous sessions, we have discussed some examples of identifying Z transform. We also plotted the ROC of obtained Z transform. From the ROC, we have concluded whether the signal is causal or anti-causal, depending on whether the ROC is exterior to circle or interior to circle. Right? So basically those signals can be termed as left-sided signal or right-sided signal. Today we will be looking at one of the example where signal can be a two-sided signal. So here is the example. Again, here you have to identify or determine the Z transform. The given discrete time signal x of n is equals to alpha to the power n u of n plus b to the power n u of minus n minus 1. So again, the given signal x of n is equals to alpha to the power n u of n plus b to the power n u of minus n minus 1. So there are two parts in this given discrete time signal. The first term, that is alpha to the power n u of n, exists for the values of n greater than or equals to 0. Right? What does it mean? This alpha to the power n u of n as the value simply alpha to the power n for n greater than or equals to 0, because for n greater than or equals to 0 this term will be 1 and otherwise it will be 0 for negative values of n. Okay, because u of n will be 0 for negative values of n. Similarly, this b to the power n u of minus n minus 1 will be having value b to the power n for n less than 0. That means for negative values of n. Because for negative values of n, if I am substituting n is equals to minus 1, so this minus will be plus 1, minus 1 will be 0, u of 0 will be 1. Similarly, for n is equals to minus 2, so it will be minus plus 2, 2 minus 1 will be 1, u of 1 will be again 1. So for negative values of n, this u of minus n minus 1 will be 1, right? And for n greater than or equals to 0, if I am substituting n is equals to 0, so it will be u of minus 1, u of minus 1 is 0. This will be 0, right? So the Z transform of x of n is given by the formula x of z is equals to summation n is equals to minus infinity to infinity x of n into z to the power minus n. Okay, so in place of x of n you can put the given signal value. Okay, that means alpha to the power n u of n plus b to the power n u of minus n minus 1. Summation n is equals to minus infinity to infinity alpha to the power n u of n plus b to the power n u of minus n minus 1 into z to the power minus n. So in place of this x of n we have substituted this signal value alpha to the power n u of n plus b to the power n u of minus n minus 1, okay, into z to the power minus n as it is. Okay, so here you can separate these two terms, right? So you can write summation n is equals to minus infinity to infinity alpha to the power n u of n into z to the power minus n plus again summation n is equals to minus infinity to infinity b to the power n u of minus n minus 1 into z to the power minus n. Okay. So as we have seen in this case, this signal will be existing only for positive values of n. For negative values of n, u of n is 0, so we can restrict these limits. So instead of minus infinity to infinity, we can write 0 to infinity. It will be 0 to infinity alpha to the power n. For 0 to infinity, u of n will be 1. So there is no need to write u of n. So multiplied by z to the power minus n. Okay. Plus summation. Again here, this u of minus n minus 1 will be 1 for negative values of n. Okay. So here again you can simply eliminate the positive values of n, that is you can eliminate 0 to infinity, you can only keep n is equals to minus infinity to minus 1. Okay, so this b raised to power n, so this will be 1 for these negative values of n into z to the power minus n. So again here for the second term you can substitute in place of n, you can keep minus n as we were seeing in the previous example discussed in the previous session. Right? I can keep n is equals to minus n. So summation n is equals to 0 to infinity alpha to the power n z to the power minus n. I will keep it as it is. Plus here I can keep minus n is equals to minus infinity to minus 1 b to the power minus n z to the power n. Okay. So again summation n is equals to 0 to infinity alpha to the power n z to the power minus n plus this minus sign I can send inside the summation values. So I'll multiply each value with minus sign. So instead of minus infinity to 1, I will indicate the 1 to infinity. Summation n is equals to 1 to infinity will be there. So b raised to power minus n z to the power n will be there. Right. So here I can take n is equals to 0 to infinity. I can take this n common, so it will be alpha z inverse raised to the power n plus summation n is equals to 1 to infinity b inverse z raised to the power n. I'll rewrite that equation, last equation, x of z is equals to, what is that? Summation n is equals to 0 to infinity alpha z inverse raised to the power n plus summation m is equals to 1 to infinity b inverse z raised to the power n. So we are seeing this geometric series where the summation n is equals to 0 to infinity a to the power n. This series is there, so you can replace it with 1 upon 1 minus a if mod a is less than 1, and if geometric series n is equals to 1 to infinity a to the power n, so you can replace it a upon 1 minus a. Okay, we have discussed these two in last session. Okay, if mod a is less than 1. So as per this two series, the first term can be simply written as 1 upon 1 minus alpha z inverse, and second term you can take it as simply this sign plus, so if you compare this second term with this second geometric series, so here in place of a, b inverse z is there. Okay, so it will be b inverse z upon 1 minus b inverse z. Okay. So it will be b inverse z upon 1 minus b inverse z. Okay. And provided conditions that mod a less than 1, that is if z inverse should be less than 1 for first term and b inverse z, mod b inverse z less than 1. So this is the required z transform and ROC again you can identify it as the values of Z. So here if I'm sending Z inverse on the right hand side, it will be 1 upon Z inverse. If I'm taking in numerator, so it will be Z. So alpha will be less than Z. So that means mod Z should be greater than alpha. And as per the second condition, this mod Z is, and I will be sending B inverse on the right hand side. 1 upon B inverse will be B simply. Okay. So these will be the values for Z. Okay, Z should be greater than alpha and less than B. But we don't know the actual values of alpha and B. So there may be two conditions. Okay, so if we try to plot the ROC of the obtained Z transform, okay, so there will be two conditions. First condition that alpha is less than B. Okay, that means alpha having smaller value compared to B, right? So as per this condition, again, when we are plotting the ROC, on x-axis we are plotting real values, on y-axis we are plotting imaginary values, right? So again, here we will be drawing, because as there are two conditions for ROC, that is mod Z values of Z should be greater than alpha, and mod Z that is values of Z should be less than B. So we'll be drawing two circles here, right? So one circle with radius alpha and second circle with radius b, but alpha is less than b, so the inner circle will be having radius alpha, and the outer circle we can draw with radius b. Okay, because b is greater than alpha. So here, as per this ROC condition, what is the ROC condition here? So ROC condition is mod Z greater than alpha, mod Z greater than alpha, and mod Z less than B. Okay. So as per this condition, so as we can see that this mod Z should be greater than alpha. That means if it is greater than alpha, then this exterior to the inner circle will be the ROC values, and mod Z less than B. So it should be smaller than this B. So this will be interior of this outer circle. So the ROC will be these values inside this circle, right? Or the part between these two circles will be the ROC. Okay, so this will be ROC indicated by this shaded or dashed region, right? Because here the values of Z are less than B and it is greater than alpha. But if we consider second condition, just for example, the value B is less than alpha. So in that case, the ROC plot will be somewhat different. So again, real values of Z will be there on x-axis, imaginary value of Z on y-axis. So again, you will be drawing two circles with first with radius b, because b is smaller than alpha now. So interior circle will be having radius b, and the exterior circle will be having radius alpha. Right. And as per our ROC condition, mod Z is greater than alpha. If it is greater than alpha, then that means it will be the exterior part of this outer circle. Right. So we have to indicate it as the exterior part of the outer circle. Right. as per second condition, mod z is less than b. So less than b means this will be the interior part of the inner circle, right? So such signal is called as there are exterior part of circle as well as interior part of circle. Similar cases here, exterior part of circle, interior part of circle. So such signal is called as what? Two-sided signal. We have seen other two categories, that is left-sided signal and right-sided signal in previous session. Okay. So this is how again you will be identifying the Z transform of the given signal. Here two different conditions were there for two different terms in the given discrete time signal x of n. Okay. So first term exists for positive values of n, while second term exists for negative values of n. So depending on that, we have substituted those values and we have written by using the geometric series form. We have written this equation of Z transform in the simplified form. And as for the ROC condition, for two different set of values, where first condition we have taken alpha less than b, in second condition we have taken b less than alpha. So depending on that, we have plotted the ROC for the obtained Z transform. Okay. So in next session we'll be discussing properties of Z transform. There are different properties of Z transform. In next session we'll be discussing the linearity property of the Z transform, and we'll try to solve some example where we'll be using the linearity property of the Z transform. Thank you for joining this session.